updating algorithm of Word2Vec did, and how it related to these more linear algebra-based methods that had been explored in a couple of decades previously. And so for the next bit, I want to tell you a little bit about the GloVe algorithm, which was an algorithm for word vectors that was made by Jeffrey Pennington, Richard Socher, and me in 2014. And so the starting point of this was to try to connect together the linear algebra-based methods on co-occurrence matrices like LSA and Coles with the models like skipgram, SIBO, and their other friends, which were iterative neural updating algorithms. So on the one hand, the linear algebra methods actually seemed like they had advantages for fast training and efficient usage of statistics, but although there'd been work on capturing word similarities with them, by and large, the results weren't as good, perhaps because of disproportionate importance given to large counts in the main. Conversely, the models, the neural models, it seems like if you're just doing these gradient updates on windows, you're somehow inefficiently using statistics versus a co-occurrence matrix. But on the other hand, it's actually easier to scale to a very large corpus by trading time for space. But at that time, it seemed like the neural methods just worked better for people. They generated improved performance on many tasks, not just on word similarity, and that they could capture complex patterns such as the analogies that went beyond word similarity. And so what we wanted to do was understand a bit more as to what properties do you need to have this analogies work out, as I showed last time. And so what we realized was that if you'd like to have these sort of vector subtractions and additions work for an analogy, the property that you want is for meaning components. So a meaning component is something like going from male to female, queen to king, or going from verb to its agent, truck to driver, that those meaning components should be represented as ratios of co-occurrence probabilities. So here's an example that shows that. Okay, so suppose the meaning component that we want to get out is the spectrum from solid to gas, as in physics. Well, you'd think that you can get at the solid part of it perhaps by saying, does the word co-occur with ice? And the word solid occurs with ice, so that looks hopeful, and gas doesn't occur with ice much, so that looks hopeful. But the problem is the word water will also occur a lot with ice, and if you just take some other random word like the word random, it probably doesn't occur with ice much. In contrast, if you look at words co-occurring with steam, solid won't occur with steam much, but gas will, but water will again, and random will be small. So to get out the meaning component we want of going from gas to solid, what's actually really useful is to look at the ratio of these co-occurrence probabilities, because then we get a spectrum from large to small between solid and gas, whereas for water and a random word, it basically cancels out and gives you 1. I just wrote these numbers in, but if you count them up in a large corpus, it is basically what you get. So here are actual co-occurrence probabilities, and that for water and my random word, which was fashion here, these are approximately 1, whereas for the ratio of probability of co-occurrence of solid with ice or steam is about 10, and for gas, it's about 1/10. So how can we capture these ratios of co-occurrence probabilities as linear meaning components so that in our word vector space, we can just add and subtract linear meaning components? Well, it seems like the way we capture these ratios of co-occurrence probabilities as linear meaning components so that in our word vector space, we can just add and subtract linear meaning components. Well, it seems like the way we can achieve that is if we build a log bilinear model so that the dot product between two word vectors attempts to approximate the log of the probability of co-occurrence. So if you do that, you then get this property that the difference between two vectors, its similarity to another word corresponds to the log of the probability ratio shown on the previous slide. So the GloVe model wanted to try and unify the thing log of the probability ratio shown on the previous slide. So the GloVe model wanted to try and unify the thinking of the probability ratio shown on the previous slide. So the Glove model wanted to try and unify the thinking between the co-occurrence matrix models and the neural models by being in some way similar to a neural model, but actually calculated on top of a co-occurrence matrix count. So we had an explicit loss function, and our explicit loss function is that we wanted the dot product to be similar to the log of the co-occurrence. We actually added in some bias terms here, but I'll ignore those for the moment. We actually added in to be similar to the log function is that we wanted the dot product to be similar to the log of the co-occurrence. We actually added in some bias terms here, but I'll ignore those for the moment. And we wanted to not have very common words dominate, and so we capped the effect of high word counts using this f function that's shown here. And then we could optimize this g function directly on the co-occurrence count matrix. So that gave us fast training scalable to huge corpora. And so this algorithm worked very well. So if you run this algorithm, ask what are the nearest words to frog, you get frogs, toad, and then you get some complicated words, but it turns out they are all frogs until you get down to lizards. So Latoria is that lovely tree frog there. And so this actually seemed to work out pretty well. How well did it work out? To discuss that a bit more, I now want to say something about how do we evaluate word vectors. Are we good for up to there for questions? It does work out, but it turns out count matrix. So that gave us fast training scalable to huge corpora. That's shown. We actually added in some bias terms here. The log function is that we wanted the dot product to be similar to the log of the co-occurrence. We actually added in some bias terms here, but I'll ignore those for the moment. And we wanted to not have very common words dominate, and so we capped the effect of high word counts using this f function that's shown here. And then we could optimize this g function directly on the co-occurrence count matrix. So that gave us fast training scalable to huge corpora. And so this algorithm worked very well. So if you run this algorithm, ask what are the nearest words to frog, you get frogs, toad, and then you get some complicated words, but it turns out they are all frogs until you get down to lizards. So Latoria is that lovely tree frog there. And so this actually seemed to work out pretty well. How well did it work out? To discuss that a bit more, I now want to say something about how do we evaluate word vectors. Are we good for up to there for questions?
We've got some questions. What do you mean by an inefficient use of statistics as a con for skipgram?
Well, what I mean is that, for word2vec, you're just looking at one center word at a time and generating a few negative samples. And so it sort of seems like you're doing something really precise there. Whereas if you're doing an optimization algorithm on the whole matrix at once, well, you actually know everything about the matrix at once. You're not just looking at what other words occurred in this one context of the center word. You've got the entire vector of co-occurrence accounts for the center word and another word. And so therefore, you can much more efficiently and less noisily work out how to minimize your loss. Okay. I'll go on. Okay, so I've sort of said, look at these word vectors, they're great. And I sort of showed you a few things at the end of the last class, which argued, hey, these are great. They work out these analogies, they show similarity and things like this. We want to make this a bit more precise. And indeed, for natural language processing, as in other areas of machine learning, a big part of what people are doing is working out good ways to evaluate knowledge that things have. So how can we really evaluate word vectors? So in general, for NLP evaluation, people talk about two ways of evaluation, intrinsic and extrinsic. So an intrinsic evaluation means that you evaluate directly on the specific or intermediate subtask that you've been working on. So I want a measure where I can directly score how good my word vectors are. And normally, intrinsic evaluation are fast to compute. They helped you to understand the component you've been working on, but often simply trying to optimize that component may or may not have a very big good effect on the overall system that you're trying to build. So people have also been very interested in extrinsic evaluations. So an extrinsic evaluation is that you take some real task of interest to human beings, whether that's web search or machine translation or something like that, and you say your goal is to actually improve performance on that task. Well, that's a real proof that this is doing something useful. So in some ways, it's just clearly better. But on the other hand, it also has some disadvantages. It takes a lot longer to evaluate on an extrinsic task because it's a much bigger system. And sometimes, when you change things, it's unclear whether the fact that the numbers went down was because you now have worse word vectors, or whether it's just somehow the other components of the system interacted better with your old word vectors, and if you change the other components as well, things would get better again. So in some ways, it can sometimes be muddier to see if you're making progress. But I'll touch on both of these methods here. So for intrinsic evaluation of word vectors, one way, which we mentioned last time, was this word vector analogy. So we could simply give our models a big collection of word vector analogy problems. So we could say man is the woman as king is the what, and ask the model to find the word that is closest using that sort of word analogy computation, and hope that what comes out there is queen. And so that's something people have done and have worked out an accuracy score of how often that you are right. At this point, I should just mention one little trick of these word vector analogies that everyone uses, but not everyone talks about along the first instance. I mean, there's a little trick which you can find in the Jensen code if you look at it, that when it does man is to woman as king is to what, something that could often happen is that actually the word, once you do your pluses and your minuses, that the word that will actually be closest is still king. So the way people always do this is that they don't allow one of the 3 input words in the selection process. So you're choosing the nearest word that isn't one of the input words. Okay, so since is that actually the word, once you do your pluses and your minuses, that the word that will actually be closest happen is that actually the word, once you do your pluses and your minuses, that the word that will actually be closest is still king. So the way people always do this is that they don't allow one of the 3 input words in the selection process. So you're choosing the nearest word that isn't one of the input words. Okay, one of the input words. Okay, so since here's showing results from the glove vectors. So the glove vectors have a strong linear component property, just like I showed before for coal. So this is for the male-female dimension. And so because of this, you'd expect in a lot of cases that word analogies would work, because I can take the vector difference of man and woman, and then if I add that vector difference onto brother, I expect to get to sister, king, queen, and for many of these examples. But of course, they may not always work, right? Because if I start from emperor, it's sort of a more of a lean, and so it might turn out that I get countess or duchess coming out instead. You can do this for various different relations, so different semantic relations. So these sort of word vectors actually learn quite a bit of just world knowledge. So here's the company CEO. Well, this is the company CEO around 2010 to 2014 when the data was taken from word vectors. And they, as well as semantic things or pragmatic things like this, they also learn syntactic things. So here are vectors for positive, comparative, and superlative forms of adjectives. And you can see those also move in roughly linear components. The Word2Vec people built a data set of analogies so you could evaluate different models on the accuracy of their analogies. Here's how you can do this, and this gives some numbers. So there are semantic and syntactic analogies. I'll just look at the totals. Okay, so what I said before is if you just use unscaled co-occurrence counts and pass them through an SVD, things work terribly. And you see that there, you only get 7.3. But then company CEO, well, this is the company CEO around 2010 to 2014 when the data was taken from word vectors. And they, as well as semantic things or pragmatic things like this, they also learn syntactic things. So here are vectors for positive, comparative, and superlative forms of adjectives. And you can see those also move in roughly linear components. The Word2Vec people built a data set of analogies so you could evaluate different models on the accuracy of their analogies. Here's how you can do this, and this gives some numbers. So there are semantic and syntactic analogies. I'll just look at the totals. Okay, so what I said before is if you just use unscaled co-occurrence counts and pass them through an SVD, things work terribly. And you see that there, you only get 7.3. But then as I also pointed out, if you do some scaling, you can actually get SVD of a scale count matrix to work reasonably well. So this SVDL is, here's how you can do this, and this gives some numbers. So there are semantic and syntactic analogies. I'll just look at the totals. Okay, so what I said before is if you just use unscaled co-occurrence counts and pass them through an SVD, things work terribly. And you see that there, you only get 7.3. But then as I also pointed out, if you do some scaling, you can actually get SVD of a scale count matrix to work reasonably well. So this SVDL is similar to the Coles model, and now we're getting up to 60.1, which actually isn't a bad score, right? So you can actually do a decent job without a neural network. And then here are the two variants of the Word2Vec model, and here are our results from the GloVe model. And of course, at the time, 2014, we took this as absolute proof that our model was better and our more efficient use of statistics was really working in our favor. With 7 years of retrospect, I think that's kind of not really true, it turns out. I think the main part of why we scored better is that we actually had better data. And so there's a bit of evidence about that on this next slide here. So this looks at the semantic, syntactic, and overall performance on word analogies of GloVe models that were trained on different subsets of data. So in particular, the two on the left are trained on Wikipedia. And you can see that training on Wikipedia makes you do really well on semantic analogies, which maybe makes sense because Wikipedia just tells you a lot of semantic facts. I mean, that's kind of what encyclopedias do. And so one of the big advantages we actually had was that Wikipedia, that the GloVe model was partly trained on Wikipedia as well as other text, whereas the Word2Vec model that was released was trained exclusively on Google News, so Newswire data. And if you only train on a smallish amount of Newswire data, you can see that for the semantics, it's just not as good as even a 1/4 of the size amount of Wikipedia data. So if you get a lot of data, you can compensate for that. So here on the right end, did you then have Common Core web data? And so once there's a lot of web data, so now 42 billion words, you're then starting to get good scores again from the semantic side. The graph on the right then shows how well do you do as you increase the vector dimension. And so what you can see there is, 25-dimensional vectors aren't very good. They go up to sort of 50 and then 100. And so 100-dimensional vectors already work reasonably well. So that's why I used 100-dimensional vectors when I showed my example in class yesterday as the sweet spot tool load and working reasonably well. But you still get significant gains for 200 and some up to 300. So at least back around sort of 2013 to 15, everyone sort of gravitated to the fact that 300-dimensional vectors is the sweet spot. So almost frequently, if you look through the best-known sets of word vectors that include the Word2Vec vectors and the GloVe vectors, that usually what you get is 300-dimensional word vectors. That's not the only intrinsic evaluation you can do. Another intrinsic evaluation you can do is see how these models model human judgments of word similarity. So psychologists for several decades have actually taken human judgments of word similarity, where literally you're asking people for pairs of words like professor and doctor to give them a similarity score that's sort of being measured as some continuous quantity, giving you a score between, say, 0 and 10. And so there are human judgments, which are then averaged over multiple human judgments as to how similar different words are. So tiger and cat is pretty similar. Computer and internet is pretty similar. Plane and car is less similar. Stock and CD aren't very similar at all, but stock and jaguar are even less similar. So we could then say, for our models, do they have the same similarity judgments? And in particular, we can measure a correlation coefficient of whether they give the same ordering of similarity judgments. And so then we can get data for that. And so there are various different data sets of word similarities, and we can score different models as to how well they do on similarities. And again, you see here that plain SVDs works comparatively better here for similarities than it did for analogies. It's not great, but it's now not completely terrible because we no longer need that linear property. But again, scaled SVDs work a lot better. Word2Vec works a bit better than that, and we got some of the same kind of minor advantages from the GloVe model.
Chris, sorry to interrupt. A lot of the students were asking if you could re-explain the objective function for the GloVe model and also what log bilinear means.
Okay. Sure.
Okay, here is my objective function. But wait, if I go, so one slide before that, right? So the property that we want is that we want the dot product to represent the log probability of co-occurrence. So and that then gives me my tricky log bilinear. So the bi is that there's sort of the wi and the wj, so that there are sort of two linear things, and it's linear in each one of them. So this is sort of like having an rather than having a sort of an AX where you just have something that's linear in X and A is a constant, it's bilinear because we have the Wi, Wj, and there's linear in both of them. And that's then related to the log of a probability. And so that gives us the log bilinear model. And so since we'd like these things to be equal, what we're doing here, if you ignore these two center terms, is that we're wanting to say the difference between these two is as small as possible. So we're taking this difference and we're squaring it so it's always positive, and we want that squared term to be as small as possible. And that's 90% of it, and you can basically stop there. But the other bit that's in here is a lot of the time when you're building models, rather than simply having sort of an AX model, it seems useful to have a bias term which can move things up and down for the word in general. And so we added into the model bias term so that there's a bias term for both words. So if in general probabilities are high for a certain word, this bias term can model that, and for the other word, this bias term can model it. Okay, so now I'll pop back, and after, oh, actually, I just saw someone said, why multiplying by the f of, sorry, I did skip that last term. Okay, the y modifying by this f of xij. So this last bit was to scale things depending on the frequency of a word, because you want to pay more attention to words that are more common or word pairs that are more common. Because if you think about it in word-to-vec terms, you're seeing if things have a co-occurrence count of 50 versus 3, you want to do a better job at modeling the co-occurrence of the things that occurred together 50 times. And so you want to consider in the count of co-occurrence. But then the argument is that actually leads you astray. when you have extremely common words like function words. And so effectively, you paid more attention to words that co-occurred together up until a certain point, and then the curve just went flat. So it didn't matter if it was an extremely, extremely common word. So then for you want to consider in the count of co-occurrence, you have to take last term. This term can model that, and simply having sort of an A in these two is as small as possible. So we're taking things to be equal. What we're doing here, like these things to be equal, what we're doing here, if you ignore these two center terms, is that we're wanting to say the difference between these two is as small as possible. So we're taking this difference and we're squaring it so it's always positive, and we want that squared term to be as small as possible. And that's 90% of it, and you can basically stop there. But the other bit that's in here is a lot of the time when you're building models, rather than simply having sort of an AX model, it seems useful to have a bias term which can move things up and down for the word in general. And so we added into the model bias term so that there's a bias term for both words. So if in general probabilities are high for a certain word, this bias term can model that. And for the other word, this bias term can model it. Okay. So now I'll pop back, and after, oh, actually, I just saw someone said, why multiplying by the f of, sorry, I did skip that last term. Okay, but why modifying by this f of xij? So this last bit was to scale things depending on the frequency of a word, because you want to pay more attention to words that are more common, or word pairs that are more common, because if you think about it in word-effect terms, you're seeing if things have a co-occurrence count of 50 versus 3, you want to do a better job at modeling the co-occurrence of the things that occurred together 50 times. And so you want to consider in the count of co-occurrence. But then the argument is that that actually leads you astray when you have extremely common words like function words. And so effectively, you paid more attention to words that co-occurred together up until a certain point, and then the curve just went flat. So it didn't matter if it was an extremely, extremely common word. So then for extrinsic word vector evaluation. So at this point, you're now wanting to sort of say, well, can we embed our word vectors in some end user task, and do they help? And do different word vectors work better or worse than other word vectors? So this is something that we'll see a lot of later in the class. I mean, in particular, when you get on to doing assignment 3, that assignment 3, you get to build dependency parsers, and you can then use word vectors in the dependency parser and see how much they help. We don't actually make you test out different sets of word vectors, but you could. Here's just one example of this to give you a sense. So the task of name entity recognition is going through a piece of text and identifying mentions of a person name or an organization name like a company or a location. And so if you have good word vectors, do they help you do name identity recognition better? And the answer to that is yes. So if one starts off with a model that simply has discrete features, so it uses word identity as features, you can build a pretty good name identity model doing that. But if you add into it word vectors, you get a better representation of the meaning of words, and so that you can have the numbers go up quite a bit. And then you can compare different models to see how much gain they give you in terms of this extrinsic task. So skipping ahead, this was a question that I was asked after class, which was word sensors, because so far we've had just one word. Sorry, for one particular string, we've got some string, house, and we're going to say for each of those strings, there's a word vector. And if you think about it a bit more, that seems like it's very weird, because actually most words, especially common words, and especially words that have existed for a long time, actually have many meanings which are very different. So how could that be captured if you only have one word vector for the word? Because you can't actually capture the fact that you've got different meanings for the word, because your meaning for the word is just one point in space, one vector. And so as an example of that, here's the word pike. Now, pike is actually a very common word, but it is an old Germanic word. Well, what kind of meanings does the word pike have? So you can maybe just think for a minute and think what meanings the word pike has. And it actually turns out, it has a lot of different meanings. So perhaps the most basic meaning is, if you did fantasy games or something, medieval weapons, a sharp-pointed staff is a pike, but there's a kind of a fish that has a similar elongated shape that's a pike. It was used for railroad lines. Maybe that usage isn't used much anymore, but it certainly still survives in referring to roads. So this is like when you have turnpikes. We have expressions where pike means the future, like coming down the pike. It's a position in diving. The divers do a pike. Those are all noun uses. They're also verbal uses, so you can pike somebody with your pike. Different usages might have different currency. In Australia, you can also use pike to mean that you pull out of doing something, like I reckon he's going to pike. I don't think that usage is used in America, but lots of meanings. And actually for words that are commoner, if you start thinking of words like line or field, I mean, they just have even more meanings than this. So what are we actually doing with just one vector for a word? And well, one way you could go is to say, okay, up until now, what we've done is crazy. Pike has, in other words, have all of these different meanings. So maybe what we should do is have different word vectors for the different meanings of pike. So we'd have one word vector for the medieval pointy weapon, another word vector for the kind of fish, another word vector for the kind of road. So that they'd then be word sense vectors. And you can do that. I mean, actually, we were working on that in the early 2010s, actually even before Word2Vec came out. So this picture is a little bit small to see, but what we were doing was for words, we were clustering instances of a word, hoping that those clusters, so clustering the word tokens, hoping those clusters of similar represented sensors. And then for the clusters of word tokens, we were also treating them like they were separate words and learning a word vector for each. And basically that actually works. So in green, we have two sensors for the word bank. And so there's one sense for the word bank that's over here, where it's close to words like banking, finance, transaction, and laundering. And then we have another sense for the word bank over here, where it's close to words like plateau, boundary, gap, territory, which is the riverbank sense of the word bank. And for the word jaguar that's in purple, well, jaguar has a number of sensors, and so we have those as well. So this sense down here is close to hunter, so that's the sort of big game animal sense of jaguar. Up the top here is being shown close to luxury and convertibles. This is the jaguar car sense. Then jaguar here is near string keyboard and words like that. So jaguar is the name of a kind of keyboard. And then this final jaguar over here is close to software and Microsoft. And then if you're old enough, you'll remember that there was an old version of macOS that was called Jaguar. So that's then the computer sense. So basically this does work, and we can learn word vectors for different senses of a word. But actually this isn't the majority way that things have then gone in practice. And there are kind of a couple of reasons for that. I mean, one is just simplicity. If you do this, it's kind of complex because you first of all have to learn word sensors and then start learning word vectors in terms of the word sensors. But the other reason is, although this model of having word sensors is traditional, it's what you see in dictionaries, it's commonly what's been used in natural language processing, I mean, it tends to be imperfect in its own way because we're trying to take all the uses of the word pike and sort of cut them up into key different sensors, where commonly differences kind of overlapping and it's often not clear which ones to count as distinct. So for example, here, right, a railroad line and a type of road, well, so that's the same sense of pike, it's just that they're different forms of transportation. And so, this could be, a type of transportation line and cover both of them. So it's always sort of very unclear how you cut word meaning into different senses. And indeed, if you look at different dictionaries, everyone does it differently. It actually turns out that in practice, you can do rather well by simply having one word vector per word type. And what happens if you do that? Well, what you find is that what you learn as a word vector is what gets referred to in fancy talk as a superposition of the word vectors for the different senses of a word, where the word superposition means no more or less than a weighted sum. So the vector that we learn for pike will be a weighted average of the vectors that you would have learned for medieval weapon sense plus the fish sense plus the road sense plus whatever other senses that you have, where the weighting that's given to these different sense vectors corresponds to the frequencies of use of the different senses. So we end up with the vector for pike being a kind of an average vector. And so if you're say, okay, you've just added up several different vectors into an average, you might think that that's kind of useless because you've lost the real meanings of the word and you've just got some kind of funny average vector that's in between them. But actually, it turns out that if you use this average vector in applications, it tends to sort of self-disambiguate, because if you say, is the word pike similar to the word for fish? Well, part of this vector represents fish, the fish sense of pike, and so in those components, it'll be kind of similar to the fish vector, and so yes, you'll say the substantial similarity. Whereas if in another piece of text that says, the men were armed with pikes and lances or pikes and maces or whatever other medieval weapons you remember, well, actually, some of that meaning is in the pike vector as well, and so it'll say, yeah, there's good similarity with mace and staff and words like that as well. And in fact, we can work out which sense of pike is intended by just sort of seeing which components are similar to other words that are used in the same context. And indeed, there's actually a much more surprising result than that. And this is a result that's due to Sanjeev Arora, Tinu Umar, who's now on our Stanford faculty, and others in 2018. And that's the following result, which I'm actually going to explain. But So if you think that the vector for Pike is just a sum of the vectors for the different sensors, well, it should be, you'd think, that it's just completely impossible to reconstruct the sense vectors from the vector for the word type. Because normally, if I say I've got two numbers, the sum of them is 17, you just have no information as to what my two numbers are, right? You can't resolve it. And even worse, if I tell you I've got three numbers and they sum to 17. But it turns out that when you have these high-dimensional vector spaces, that things are so sparse in those high-dimensional vector spaces that you can use ideas from sparse coding to actually separate out the different sensors, providing they're relatively common. So they show in their paper that you can start with the vector of, say, Pike, and actually separate out components of that vector that correspond to different sensors of the word Pike. And so here's an example at the bottom of this slide, which is for the word tie. Separate out that vector into 5 different sensors. And so there's one sense is close to the words trousers, blouse, waistcoats, and this is the sort of clothing sense of tie. Another sense is close to wires, cables, wiring, electrical, so that's sort of the tie sense of tie used in electrical stuff. Then we have sort of score line goals, equalizer, so it's the sporting game sense of tie. This one also seems to, in a different way, evoke sporting game sense of tie. And then there's finally this one here. Maybe my music is just really bad. Maybe it's because you get ties and music when you tie notes together, I guess. So you get these different senses out of it. Hi everyone, I'll get started. Okay, so we're now back to the second week of CS 224N on natural language processing with deep learning. Okay, so for today's lecture, what we're going to be looking at is all the math details of doing neural net learning. First of all, looking at how we can work out by hand gradients for training neural networks, and then looking at how it's done more algorithmically, which is known as the backpropagation algorithm. And correspondingly for you guys, well, I hope you remember that 1 minute ago was when assignment 1 was due, and everyone's handed that in. If by some chance you haven't handed it in, really should hand it in as soon as possible. Reserve those late days for the harder assignments. So, I mean, I actually forgot to mention, we actually did make one change for this year to make it a bit easier when occasionally people join the class a week late. If you want to this year in the grading, assignment 1 can be discounted and we'll just use your other 4 assignments. But if you've been in the class so far, for that 98% of people, well, since assignment 1 is the easiest assignment, again, it's silly not to do it and have it as part of your grade. Okay, so starting today, we put out assignment 2, and assignment 2 is all about making sure you really understand the math of neural networks and then the software that we use to do that math. So this is going to be a bit of a tough week for some. So for some people who are great on all their math and backgrounds, they'll feel like this is stuff they know well, nothing very difficult. But I know there are quite a few of you who this lecture and week is the biggest struggle of the course. We really do want people to actually have an understanding of what goes on in neural network learning rather than viewing it as some kind of deep magic. And I hope that some of the material we give today and that you read up on and use in the assignment will really give you more of a sense of what these neural networks are doing and how it is just math that's applied on a systematic large scale. that works out the answers, and that this will be valuable and give you a deeper sense of what's going on. But if this material seems very scary and difficult, you can take some refuge in the fact that there's fast light at the end of the tunnel, since this is really the only lecture that's heavily going through the math details of neural networks. After that, we'll be kind of popping back up to a higher level, and by and large, after this week, we'll be making use of software to do a lot of the complicated math for us. But nevertheless, I hope this is valuable. I'll go through everything quickly today, but if this isn't stuff that you know backwards, I really do encourage you to work through it and get help as you need it. So do come along to our office hours. There are also a number of pieces of tutorial material given in the syllabus. So there's both the lecture notes, there's some materials from CS231. In the list of readings, the very top reading is some material put together by Kevin Clark a couple of years ago, and actually that one's my favorite. The presentation there fairly closely follows the presentation in this lecture of going through matrix calculus. So personally, I recommend starting with that one, but there are 4 different ones you can choose from if one of them seems more helpful to you. 2 other things on what's coming up. Actually, for Thursday's lecture, we make a big change, and Thursday's lecture is probably the most linguistic lecture of the whole class, where we go through the details of dependency grammar and dependency parsing. Some people find that tough as well, but at least it'll be tough in a different way. And then one other really good opportunity is this Friday we have our second tutorial at 10 a.m., which is an introduction form of classifier that we can use for it. So the task of named entity recognition is a very common basic NLP task, and the goal of this is you're looking through pieces of text and you're wanting to label by labeling the words which words belong to entity categories like persons, locations, products, dates, times, etc. So for this piece of text, last night Paris Hilton wowed in a sequin gown, Samuel Quinn was arrested in the Hilton Hotel in Paris in April 1989. Some words are being labeled as named entities as shown. These 2 sentences don't actually belong together in the same article, but I chose those 2 sentences to illustrate the basic point that it's not that you can just do this task by using a dictionary. Yes, a dictionary is helpful to know that Paris can possibly be a location, but Paris can also be a person name. So you have to use context to get named entity recognition right. Okay, well, how might we do that with a neural network? There are much more advanced ways of doing this, but a simple yet already pretty good way of doing named entity recognition with a simple neural net is to say, well, how might we do that? Right. Okay, well, how might we do that with a neural network? There are much more advanced ways of doing this, but a simple yet already pretty good way of doing named entity recognition with a simple neural net is to to say, well, what we're going to do is use the word vectors that we've learned about, and we're going to build out a context window of word vectors, and then we're going to put those through a neural network layer, and then feed it through a softmax classifier of the kind that we, sorry, I said that wrong. Then we're going to feed it through a logistic classifier of the kind we saw when looking at negative sampling, which is going to say for a particular entity type, such as location, is it high probability location, or is it not a high probability location? So for a sentence like the museums in Paris are amazing, to see, what we're going to do is for each word say